Welcome to This Explainer. Today, we're going to deeply unpack the math and concepts of electrostatics, step by step. And listen, my goal here is to explain everything conceptually and mathematically so you truly grasp the mechanics at play. We're going to dive deep, we're tossing the script and the notes aside, and we'll take whatever time we need to build a complete, intuitive understanding of these invisible forces. Sound good? Let's get into it. Here's our roadmap for today. We'll be hitting 5 main areas: the nature of charge, forces and Coulomb's law, mapping the electric field, flux and Gauss's law, and finally, we'll wrap up with the electric dipole. Okay, let's dive straight into section 1, the nature of charge. So there are a couple of fundamental properties of charge we absolutely need to lock in right away. First up is quantitation. This means charge isn't some continuous, infinitely divisible fluid. No, it only ever occurs in distinct integer multiples of a fundamental value E, which is 1.6 times 10 to the negative 19th coulombs. Think of it like walking up a staircase rather than walking up a ramp. You can't stand on half a stair, right? Second, we absolutely have to highlight the principle of conservation. The net charge on an isolated system is always conserved. You can shuffle charge around, like when two metallic spheres make physical contact, but you can literally never create or destroy it out of nowhere. Moving right along to section 2, forces and Coulomb's law. So the crucial point here is that Coulomb's law describes a non-contact force. It's action at a distance. The equation basically tells us the force is directly proportional to the product of our two charges and inversely proportional to the square of the distance between them. That's the classic inverse square law at work. And hey, notice that constant K in there? It includes epsilon naught, which is the permittivity of free space. You can think of that term as a measure of how much resistance a pure vacuum offers to the formation of an electric field. Pretty wild to think about empty space having resistance, right? But honestly, what happens in the messy real world? We rarely just have two isolated charges sitting all alone. That's exactly where the principle of superposition comes in. If we slowly walk through the vector sum equation here, you'll see the net force on a particular charge, let's call it Q, is simply the sum of the forces from Q1, Q2, Q3, and so on. The absolute brilliant part about this, the presence of all those other charges doesn't alter the individual force between any two specific charges at all. They don't interfere with each other, they just simply add up as individual vectors. All right, section 3, mapping the electric field. So what exactly is an electric field? Well, it's defined as the electrostatic force experienced per unit charge at a given point in space. And this completely shifts our perspective. Instead of just picturing charge A pushing charge B from a distance, we are now looking at how charge A physically alters the very fabric of the space around it. It creates this invisible web, a field, that charge B then inevitably interacts with. To really visually anchor this whole concept of electric field intensity, just think about what happens when you bring a tiny positive test charge into the space. We can actually map the field lines. For a positive point charge, those field lines radiate spherically and symmetrically outwards. For a negative charge, the lines pull radially inwards. And the density of those lines, how packed together they are, gives us a direct, intuitive visual of the field's actual strength at any given point. Now that works perfectly for a single dot of charge. But what happens when charges spread across a continuous shape, like a long line, or a ring, or a flat plane? Well, we can't just use simple point algebra anymore. We've got to bring in the heavy hitter, calculus. And this brilliantly illustrates exactly why. We're looking at the derivation for the electric field due to a ring of charge. To solve this, we have to take a tiny differential element of the ring, just a microscopic slice we call dq. That tiny slice creates its own tiny electric field, dE. Now, because of the ring's perfect symmetry, all the vertical components of that field cancel each other out entirely across the circle. Poof, gone. That leaves us with only the horizontal components, dE cos theta. By integrating those horizontal components all the way around the loop of the ring, we arrive at the final, beautifully derived equation at the bottom for the total electric field along the axis. It's kind of like a mathematical symphony when it all comes together. And we can take that exact logic a step further. Think about a solid disk. It's essentially just a continuous collection of concentric rings, packed super tightly together. By methodically guiding ourselves through these integration steps, we're basically summing up all those rings, starting from a radius of 0 all the way out to the full radius, capital R. I know, it looks a little mathematically heavy on the screen, but conceptually, we are just stacking an infinite number of rings to find the total field of the entire disk. Makes total sense when you break it down like that.
Let's move to section 4 and see how this builds into something amazing: flux and Gauss's law.
Okay, first things first, we need to clarify what electric flux actually is. It's defined as a measure of the number of electric field lines crossing a given surface area. Now, do not let the word flux intimidate you. Conceptually, we are simply intuitively counting invisible lines as they pierce through a designated boundary in space. That is the whole shebang.
Which brings us to the absolute powerhouse, the fundamental formula for Gauss's law. It states that the net flux through any closed surface is directly proportional to the total charge enclosed by that surface divided by epsilon naught. Guys, this is an incredibly elegant shortcut. Instead of dealing with horribly messy vector integrals for complex continuous shapes, if you know the charge trapped inside a closed bubble, you instantly know the total field escaping it. It's a real game changer for solving these problems.
Let's meticulously narrate how this plays out for a uniformly charged solid sphere. Notice how we mathematically construct an imaginary bubble, a Gaussian surface. We have to do this for two specific scenarios: inside the sphere where our radius r is less than the sphere's radius r, and outside where r is greater than r. Inside the sphere, the enclosed charge depends on the volume density, so the field actually increases linearly. But step outside? The entire sphere acts exactly like a single point charge, concentrated right at the very center. It's almost like a magic trick, but it's just really good math.
Now contrast this with the derivation for an infinite cylinder of charge. By changing the geometry from a sphere to a cylinder, we naturally change the area component of our flux equation. Instead of a sphere surface, we use the curved surface area of the cylinder, which is 2 pi RL. But here is the beauty of it. The core principle of Gauss's law remains completely identical. We find the enclosed charge, we divide by epsilon naught, and we solve for the electric field perfectly. The geometry changes, but the golden rule stays exactly the same.
All right, we've reached the peak of our conceptual pyramid. Section 5, the electric dipole.
So notice the setup here: two equal and opposite charges, positive Q and negative Q, separated by a very small distance, 2L. This specific paired arrangement is called a dipole, and the electric dipole moment, which we represent with P, is a vector quantity that inherently points from the negative charge straight over to the positive charge. It's a fundamental property that you are going to see absolutely everywhere in chemistry and physics, so it's absolutely crucial to wrap your head around it. If we want to find the electric field along the axial line of this dipole, we just slowly walk through the algebraic derivation. We actually use the principle of superposition that we learned about earlier. The net field is found simply by calculating the field from the positive charge and then subtracting the field from the negative charge along that exact same axis. Since the physical distances to any given test point are slightly different for each charge, the fields don't totally cancel out, meaning there's a net field that remains. Now, what's really fascinating is what happens when you take that dipole and drop it into an external uniform electric field. The uniform field pulls the positive charge in one direction, and it pulls the negative charge in the exact opposite direction. So the net force is zero, meaning the dipole isn't going to translate or slide across the page, but because those forces are physically offset from one another, they create a rotational torque. The dipole will literally spin to perfectly align itself with the field. How cool is that?
So, what does this all mean for us? We've traced the path all the way from the quantization of a single microscopic particle up to the rotational torque acting on complex molecules. And this leaves us with a massive, mind-bending question. How do these tiny, invisible electrostatic forces scale up to shape the macroscopic architecture of the entire universe around us? The math we just deeply decoded together, it is the very language dictating how all matter interacts, binds, and behaves. Keep exploring, keep questioning, and keep looking for the invisible forces that shape our reality. Thanks for joining me on this explainer.